This is a video for AQA Discrete Mathematics, Linear Programming Section 2.1, which is introducing the simplex method for solving linear programs. In previous videos we've seen graphical methods for solving problems which have got two variables, x and y. The simplex method, importantly, is an algebraic way, so it doesn't require any graphical work. And because of that, it can be applied to problems where we've got more than two variables. So we could have x, y, and z, which if we're doing that graphically will require a three-dimensional graph. Possible, but quite difficult, so x, y, and z. But the simplex method can have as many variables as we wish. It's an iterative method which looks to maximize the objective function that we're trying to find. And because it's iterative, it can then be computerized quite straightforwardly. Now, to understand how it works, we're going to first of all look at it in action for a problem where we've got two variables, x and y. Here's a fairly standard type of question then with two variables. You can see we've got the objective function p that we're trying to maximize, and then a set of three constraints, and of course then the non-negativity constraints, which are always going to be present in this type of problem. We can put all of those onto a graph, and you've seen this in videos before, and we know then that the solution is going to be at one of the vertices of the feasible region. We know that each of these vertices is the solution to simultaneous equations. So for example, that one there is the equation which is given by 2x plus 3y is less than or equal to 30, or equal to 30 for the equation. So this one here, the blue one, and the line which is x is equal to 0. So that point there is the solution of those two equations. And likewise for any other vertex. We can see that we've got two lines crossing there. So what the simplex method does, it systematically, starting at the origin, moves around the edge of the feasible region, visiting each of these vertices and checking whether improvements can be made to the value of the objective function. So the way that the simplex method works is that the coordinates are found by solving simultaneous equations, and we do this with what's called a simplex tableau. It's a way of representing the equations into a table, and then using operations on that table, solving the equations until we find the optimal solution. In two dimensions it's quite straightforward, of course, graphically, but we consider what would happen if we had three variables and therefore a three-dimensional space, and what would our problem now look like. Well, here's an example where we've got a constraint 3x plus 2y plus z is less than or equal to 6. And as we do with the two-dimensional case, we need to replace that with an equality, and we get 3x plus 2y plus z is equal to 6. And of course now you'll recognize that as being the equation of a plane. So in three-dimensional space we can represent that plane as on this diagram here. If we had more constraints, then we'd have more planes added onto our diagram. Here's an example then when we've got all of the constraints listed on the right hand side, and you can see that the planes have divided the three-dimensional space, and inside that, although we can't actually step inside it, inside there is our feasible region, which is now a three-dimensional space. But as before, the optimal solution is at the vertices, and we can find those by by finding the intersection points of the planes. And the simplex method does exactly the same as in the two-dimensional case. It starts off at the origin and moves around the three-dimensional space, checking the value of the objective function at each of the vertices to see when an optimal solution has been arrived at. The objective function, which, if you remember, with a two-variable case is a line, is now also a plane, and what we can do is move that plane further away from the origin and look at which of the vertices the plane leaves the feasible region. However, that's not going to be possible to do in practice, so the simplex method gives us this algebraic way of doing that. Well, that concludes this introduction to the simplex method, and in the next few videos we'll be looking at how it is actually done in practice. So we can't, in summary, we can't solve linear programming problems with three variables in practice graphically, so that the algebraic method is essential, and then we can extend that to more than three variables, which of course can't be done in a graphical way. Because we've got the simplex method, which is then something that can be used by computer, it's far more efficient to solve using this sort of method.